I'm John Wilker, the organizer of 360 IDEP. I hope you enjoy this session recording, but first I wanted to mention one thing. We've served the community since 2009, and over the past few years we've had to take on debt in an effort to keep the conference alive. After several unforeseen challenges, not the least of which is a pandemic of indefinite duration, we've had to make the hard choice to end the conference as we're now facing over $100,000 in debt. As a result of requests from the community of how they can help, we've created a GoFundMe campaign. If you're inclined and able, please consider donating to help keep 360 IDEP going. The QR code after this will link you to the campaign. Thank you. Enjoy the recording.
So there's a download URL if you'd like to follow along or just even use it later. It's a workspace with just 2 playgrounds in it. One of them's blank, and one of them has this presentation, so you can follow along with that. Or you can just watch and deal with this later. Should I go? All right. So there's a talk on real physical computing in Swift, and it's not necessarily a talk on scientific computing, but I hope to make the point that this is something that might have a much broader appeal, even if you don't think of yourself as even having to deal with numbers per se on a constant basis. In 1983, Air Canada Flight 143 was trying to go from Ottawa to Edmonton in Canada, and it ran out of fuel. Fortunately, the pilot knew how to take a big plane with lots of passengers and land it, and he glided the plane down in Gimli, I think it was Manitoba, and it was forever known as the Gimli glider, where he got everybody safely landed. In 1985, there was a test of the Star Wars defense system, and they had a mirror on the shuttle that was part of the test. And they had to aim the mirror at a certain place in order for the test to go off without a hitch. Now, they sent on the ground a command to point the shuttle's mirror at 10,023 nautical miles above Maui. And the software on the shuttle was expecting things to be in feet. So it pointed the mirror at 10,023 feet above Maui. And so when they're getting ready for the test, they're looking up, and the space shuttle flew upside down over Maui. It's a tribute to the rest of the software that it said, oh, I'll point you wherever you want to go. So there's a red dot in the sky that turns out to be a planet, and we were going to send a Mars climate orbiter that we were going to orbit around the planet in 1999. And toward the end of this was a joint mission between the European Space Agency and NASA. And at the end, as it approached the planet, they were going to give it the information to safely arrive in orbit over the planet. And this is what happened. It landed and crashed onto Mars. The total bill for that whole thing in today's money is roughly $500 million was lost on that one. It's very tragic. All 3 of these were caused by simple unit mix-ups. Things that should have been caught and that everybody on all the software teams believed they did have taken care of, and it wasn't going to be a problem. People who wrote software and believed everything was fine. So always be wary of this thought. GitHub. There was a study done a few years ago of 213 different systems, comprising of about 1 million lines of code. And they used a system that was able to look inside of the code, and these were very mathy systems. But this did an analysis of how different functions and different calling sites were expecting to see numbers in certain units, and was that being fulfilled? And they found that approximately 11% of them had errors they did not know about. So whatever unit tests and everything, the systems are all believed to be working fine. Closer to home, this is the function I wrote a few years ago, roughly. This is very schematic. I had a function where I was expecting both a frequency and a loudness level. And I was using Swift's type alias to point to an underlying type of float. Later on, in a different object, I'm calling this thing, and I switched the values. Now Swift just is like, oh, you're passing two floats to a function that takes two floats? No problem. So it didn't say anything, and it only took me tracking down a very small error. Anytime you sometimes get a very small numerical error and you chase it all down, there's a real problem often right at the end of that, and it's well worth chasing after. But I didn't even know it existed for a long time. This is what happens as a matter of course in most programming. If you have some kind of measurement that you're dealing with, people will pick an underlying base type of like integer or a decimal or a float or double, and they will put a comment to themselves about what they chose. And they hope, I guess, on some level that 3 years from now, when a junior dev is working on this in a part of the company that you don't even know about, that they'll chase down the source code and look at your comment to find out that it was in meters. And this is something I call comment-based typing. This is rampant, and it's kind of a silent scourge that happens in programming. And some people try to address it this way, which is like you try to embed it into the names of your variables. Like, oh, now I'll never not know, because it's distance in meters. But what happens when you start dealing with quantities that are more complicated than just this? So these are from a couple of textbooks written for scientific Python. And here, they're just flatly admitting there's really nothing that can be done here, especially probably at the time. There are now systems for Python, but their advice was, comment. And look down at the lower one where things get really, magnetization saturation with all this stuff. And they're leaving it to a little comment at the end of the line to know what units you're working in. And you might say to yourself, well, okay, but we're always using, SI units and stuff, and you might think that, but somebody's going to be like, oh, well, I'm using grams. You're using kilograms. Somebody's not going to be on the same page. This is, you can download NASA code. It's a public enterprise. You own everything NASA makes. So you can download code. This is real NASA code from a mission. This is their comments on what these units are, because they've learned their lessons. They're not going to mix up units anymore. They're going to comment more. So this is not a great solution to this. This is these are a few examples here. This is from page 1 of a book on doing computational numerics. It's an introduction to get your feet wet and to do a simple chemistry equation and to write down the units in here. I looked at this because I was using textbooks to debug the system that I'm going to be talking to you about today, and this one flummoxed me because I kept getting the wrong answer over and over. Until I found out that their example on page 1 was actually wrong. The real answer to this is, instead of a room temperature of 17 degrees that you solve for, the temperature is actually a plasmatic 290,000 Kelvin. And this book is in its 10th edition, and I feel bad for the students who probably ran into it and blamed themselves every time they got it wrong. And it also leads to a common thing, which is where people will make a little bit of code, they'll be off by 1,000, and they say, I'm not sure what I did wrong, I'm going to divide by 1,000, and I'm just going to hard code that. So there are a lot of fudge factors in code, and it's disturbing, but it's real. And I'm not trying to shame this. I'm actually trying to point out how easy it is, even when you think you're doing everything right. Because look, everything is labeled with the units, except for the gas constant. And yeah, you could make up a unit that will give you that result down there, but that's not usually that. If you use the gas constant, you will not get that answer. So this is an amazing thing. There are 7 fundamental types of measurements, which is kind of nuts. There's length, time, mass, current. not all the emojis could work with me here. Mass, yeah, current, amount of stuff, temperature, and luminosity. And these form sort of like the basic physical dimensions that you can derive almost every single other kind of measurement, at least as far as what kind of units they're using. You can, so if you have a unit of force, well, it turns out you can break that down into these 7 fundamental ones. And don't worry about the details, it gets crazy. And not only that, but there are like millions and millions of different ones, and you can make up your own at will, right? But it's a sort of like, it's a unbelievable achievement of the 20th century that this even happened, and it's sort of a silent, amazing thing in science that it got to the point that they could have these coherent systems where they worked out that you could start with these 7. And it's still evolving. As of 2019, we are in the 9th edition of the SI system. It's not just we have the SI system or we have the English system or something. It's that it's constantly evolving, and there's a 10th edition and 11th edition being planned where they're going to take more things into account. This is a thing ongoing, and it's an amazing achievement. It makes modern engineering possible. So it doesn't capture absolutely everything, and even in the 10th edition, they're considering adding a few things like angles, and there's an issue over dimensionless constants that I will go over. And just really quickly, here's some things to consider when thinking about what would be done if you were able to say these types of things in programming. There's an algebra to how these things can interact, where you can add, what kinds of things can you add and subtract together. This is just a very simple thing. What things can you multiply and divide? And it's not always completely obvious. Like, first of all, any compiler will be happy with all of these, because just, you know, doubles, and you can do all of that stuff. So what kinds of things actually would be meaningful are only some of these things. Adding masses together, you can't add force and mass meaningfully. You could probably try to dream up something there, but it won't be particularly helpful for you know, these kinds of computing. And I don't even know what that last one is. It's just made up, but you can do it, and it will be meaningful, and it's okay. Multiplication, you can kind of mix and match your own kind of stuff. So one very straightforward result that we've probably all learned at some time in school is you've been told to, if you have an equation, one way to check if your equation even makes sense is to balance your equation. Like, check out the units, like mass and acceleration. That's some kind of stuff length over time squared. And so that's the right side of the equation. And you got to make sure the left side of the equation, force happens to be in these units. They match, the whole thing makes sense. So this kind of stuff can be done in software and can alert you either at runtime or compile time, depending on how it's implemented, that you have a problem that, again, if you just do it in raw math, your compiler is going to be happy with anything you throw at it as far as making some kind of equation. So here's what I wanted from a programming language, and from Swift in particular. I wanted to be able to say that something was 12 feet if I'm going to measure a distance. I'd like to be able to say that I could just tack on another 7 inches on that. And I want to be able to do something unique, something like joules per hectare. I don't know. I'm like doing some kind of farming thing efficiently, and I want to know how much energy I'm wasting per unit area or something. And I want arbitrarily novel things, because I don't know what I'm going to be programming against. And, you know, how hard could that be? And if you have never read this comic, this is a good time to read it now. It's from the great XKCD series. And so this is the worry, right? If you're going to make your own system that's going to do something like this, this is the first thing that should come into your mind. Now, does anybody have any clue as to how many systems there are in existence that are trying to solve this kind of problem in programming? Correct. There are roughly 4,000. Okay. So now the happy news is there are only about a couple hundred that are actively being used. And really, on a per language level, there's a little bit of like evolution where 1 or 2 of them usually is being actively maintained per language. So, Python, I think, has like 3 or 4 that are pretty good, but like most people use just a couple of them. And, Ruby, Rust, basically any language you can think of. Julia, and I'm going to throw my hat in the ring as well. This whole subject intersects with interests of mine that have to do with both philosophy of science, science measurement, which has a very interesting history, and then just practical programming, where I have things that I want to get done, and I want things that the language can help me figure out what makes sense and what doesn't. Now, Apple did a great thing in 2016. They came up with this measurement framework that's really quite impressive and unique. It's very readable, it's very elegant, it's available on all your iOS and Mac platforms, it's on your watch, and you can take units in a certain measurement, in this case, frequency. You can convert them to like frames per second or something like that. It's very readable. You can hand this to junior programmers and they can fully understand what's going on. It's a library. It's not specific to any language. It was originally, I'm sure, made for Objective-C and then used in Swift as well. So it has no language level support for it, which is fine. A lot of good things happen at the library level. It has some very unique things, though. It can localize, to like 62 languages or something like that. So if you want to write 45 meters per second squared in Korean, it's taken care of. And the amount of love that goes into this framework is impressive. And there's a great session in the 2016 WWDC that's well worth watching on some of the features. It's wordy, but it's clean and it's readable. And there are also a ton of different conversion factors and unit types that they make available. They really gave stuff that even goes beyond the SI standard per se that might be helpful. So one thing it can't do is mix units. So it can't work as a full-featured system that can help you with dealing with different kinds of units. So if you want to do something like this, you have to do it by hand. You have to make a function that takes one of the things, takes the 2 arguments, makes a new unique argument that you pass back. Now, the nice thing is the typing is handled really well that way. But it's inconvenient and it's wordy, and this is not very well adopted by people. So Apple's had this around for a while. I know very few people who have this in any of their code. And we'll address some of the other stuff about why that might be true. Now, I've had ideas that I've been rolling around in my head about a math physical framework of some kind that could do a lot of things for me. I'd also like to clean up the measurement system so that it works. Swift has some really unique things about its expressiveness that I think the measurement framework could really benefit from. And then I also have a personal set of utility tools that I've made over the years that happen to work perfectly for this kind of system. So I made it so that like all you got to do is import physical. If you use in that the workspace that I addressed at the beginning, if you hook up the Swift package, you add the package. All you got to do is say import physical, and then it's just available. You don't have to use it, don't have to fully adopt it, but these are the ideas behind it. Apple's idea was very simple. This is Apple's basic concept behind measurement. It was just going to couple a number and a unit and have them travel around together as a pair, right? This is a very simple idea, and it's powerful because it's simple and clean, and it does there's some details in there, but this is the basic idea. Now, I'd like to make use of Apple's very rich infrastructure and thousands of hours of engineer time that goes into their system as well. It's like having your own fleet of like Apple engineers helping you build the little thing that you're building, but all of a sudden you look much larger when you're seeing the capabilities that you gain. So building on top of Apple's system is something that I hope this is a bit schematic. It's a little more complicated. You can look at the source. It's something that I try to make equally elegant on some level, and it'll evolve a bit. But this is the basic idea. In addition to just the value itself and a dictionary of different kinds of values that can hold a very rich situation that you might have gotten yourself into. It also, I put sig figs here, but it has an ability to track precision of the measurements, because real-world measurements aren't arbitrary decimals that go out 16 places. Like, you divide 1 over 3, you have a third of something, you usually don't actually know it to 16 decimal places, right? So this is also a problem in programming where programmers have no idea that they're claiming a higher precision than they realize, and they give results to people that have no merit based on the data that they've been given. So this is a system where there are a lot of opportunities actually in a unit system to take care of a class of problems that aren't just about units. So it's a way of protecting, you can build in interesting new features. So Apple provides these types of units, very rich class, lots of specific kind of units behind every one of these. So just, as far as like duration, it's got, seconds, minutes, hours. And for electric current, it's got amperes and other units. And, mass, kilograms, pounds, all that stuff. So in the physical framework that I'm presenting, it not only adds many units that were not included, because Apple makes their system intentionally expandable so that you can enhance it, which is great. So it takes a bit of advantage of that and adds a bunch of things to the built-in ones, but also adds these dimensions as well. So these are things that are used actively by people in engineering, and the above set is not quite enough to do what you might want to do. So a lot of common concerns in biology, chemistry, and physics and other areas, but also some things that are maybe more useful for doing like 3D graphics, like solid angle and such like that. So this is the goal of this system, and this is the goal of basically any system I try to get involved in. I want the end result to be more readable code than you started with. I want it to be less buggy code, not just because it's more readable, but because it'll actually help you catch stuff that you had no idea was a problem. And I want it to be easy to use. I want it to be not a hassle to somebody to be like, I got to learn the whole thing. I don't know if you've ever tried to use something like Boost or some of these other systems, but you got to get into it before you can actually start really doing anything with it. And I want something that's actually not that way, ideally. I want it to be used where you desire to use it. So I always favor a light touch. You don't have to buy in. You don't have to convert code. You don't have to change anything about what you're doing. It's simply an opportunity that you can use as you feel like it. And then lastly, so the system presents new opportunities that we can dream up, that we can take further into the future. So there was a study done actually fairly recently. It's amazing how, unit systems, people have been trying to put these things into place since the 70s in, Pascal and Ada and lots of languages that are not major languages now, all the way up to the present day. And there's a rich literature that I've fallen down the rabbit hole in reading. But only recently did somebody actually study exactly why people don't adopt it. Because I fully, that is the situation. Most people do not use these systems. And so I view it as a part of evolution of languages in general. I think the languages in the future will have these kinds of things built in. And I'm throwing my hat in the ring toward that evolution, nudging it ever so politely, hopefully in that direction. But the main reasons people don't adopt it is, one, they don't know it exists. So if you get nothing else out of this talk, just knowing that unit systems that can help with a broad class of problems, that they even exist, is good to know about. So maybe you're not into it, but maybe somebody else is, and it can help them. The other main reason people don't adopt them is because they don't believe it applies to their code. I don't write code that needs any of this stuff. And often that could be true if you're just like as one of the talks said, just parsing JSON and pushing it to the UI or something like that. But even if you're doing something as simple as rotating an animation or something, it's a very low threshold at which you might want to use something like this. And there might be things you do that you don't even realize actually could benefit from something like this. And then the last thing is worry that you have to rewrite code. And so that's a top of my list thing that is not to demand that code have to have some deep rewrite so that you have to go back in and you're already 500,000 lines of code into some project. And anyway, so this is the idea. So this was originally going to be a live demo, and then I timed it out, and you were going to be here far too long. So I have instead opted for just showing you what I was going to walk through. The only thing that gets missed by doing it this way is the lovely autocomplete, which I gotta say is a real plus when you're actually programming. A rich autocomplete is a wonderful experience. If you try the playgrounds that I've set up, you'll see how nice this works. So this is an example. This is all working Swift code that you can run right now. So I can make distances in centimeters and feet. I can add them together. By default, if you add things that are in different types of units, it will revert to the SI unit so that you can see it in meters. And then from there, you can change it to anything you like. So this is basic stuff that could be done with the measurement framework for Apple. So nicer syntax, maybe. Speed of kilometers per hour. But then down here, I can start dividing them and coming, and notice that distance over speed comes out to seconds. So it didn't just make a mangle of units. It intelligently figured out that the end result of that was a time. And now you have something in a time. And you can convert it to hours. You can convert it to anything you'd like. Might fail, but if you know that you want that thing in hours, you can convert it to hours. And then there's a convenience syntax of an arrow, an actual arrow, not the dash angle hack that we use in languages often. I use a custom keyboard for mine, and I have an arrow on mine. Unnecessary if you want to use the .to because you've decided ASCII till death, that's fine. So here is an example of chaining units. So once you have something in a unit, and let's say you want to even make up units or something like this, you can simply daisy chain the units. And if you have an exponent for one of the units, you can go ahead and put that in there. And now you have kilograms, meters per second squared, which happens to be a force measure. But and since it is a force, I can ask for that in newtons and get the answer in newtons. I can get meters over seconds by putting the -1 in there, but there are some convenience things that have been added to this where you can simply use the slash with the dot. The units always have to have the dot as part of the chaining. The slash, there are many clever, wonderful little tricks you can do with infix functions in Swift. And so basically what's happening, by the way, how this works is when you put something like 1 kilograms, takes a double, and that postfix function turns it into a physical object. And from there, you can start manipulating it and sort of like, so when something changes type, it sort of infects the rest of the line so that everything continues to be a physical object, and you can do different kinds of manipulations on it. It even does the 12 meters per second per second. That's the way a lot of engineers would prefer that to happen. So really what happens after that slash is you're on the denominator for now on, and you stay there. So you don't have to put that second slash, but that is often how people speak about acceleration, and this matches that expectation. Here is a little more complicated, and it shows off a couple of things. So if I put some kind of radius, and I'm doing typical calculations for area and volume. And you can either use pi, pi, or you can use the Greek letter pi. And I'm also, there's a convenience that's always been driving me nuts. Often in equations, you have 2 pi, 3 pi, something like that, 4/3 pi. Well, I want to make, so I have a little extension to int, where you can just add a pi to int, and it'll give you back a double, which will be what you expect it to be. It's a convenience thing. It's little syntax sugar. So, and I can see people maybe balking at some of these things, and I consider them all open for discussion. This is my opening salvo, and people can take from it what they will. And also a real exponent function, because pow with 2 arguments is awful to read, and it's very not how you're expecting this. And now the only downside on that is that operator is being used for bitwise operations in Swift, They didn't check with me first on this. Like, most people don't actively do a lot of bitwise stuff, and I feel like they should have maybe given more consideration to doing this with the floats and doubles. But whatever. So the only thing the reason I bring that up is sometimes you have to put something in parentheses because otherwise Swift might think that you're trying to do a bitwise operation. Doesn't often come up, but it's debugging tip. So under the hood, I mentioned that these physical things have a value. So if you ever just need the raw value, you can ask for it. So volume's value is that. And as you do these computations, everything's being done in doubles along the way. But at the top, there's a clever, I think it's clever, little algorithm that keeps track of that double that you wrote literally at the top, and it knows that the significant figures to it are 4. And so when you do calculations further down, and you do distance divided by 3, the answer is out to 4 sig figs. Well, that's out to 5 sig figs. Right, because I asked for it to 5 sig figs just above it. But up there where it says volume and area, the numbers are to 4 sig figs. And so you're maintaining your precision based on the actual number that you gave it. If you need it to know that you've got higher sig figs, if you know 4 meters and you have some insane instrument that knows that to 5 sig figs, all right, you got me. Go ahead and do that. But just put it in the code. And then you also have it hard-coded, and the expectations are there for people who read the code later and use it later. And you can get the significant value out. So usually I just use it for presentation because, like I say, it carries the doubles through all the calculations as it goes. And then later, if you need it to just that precision, you can ask for it. This is wonderful, not actually doing the live coding thing. It saves on all this time. So here are some various expressions, and this is meant to point out that there are some conveniences and a few alternate ways to write stuff, because if something is done, if you make one syntax for something and it's not something you enjoy doing, and you're stuck with it, I don't consider that quite optimal. You don't want a million ways to write something, but sometimes you want a few options. So in here, this is basically 5 different ways to write grams per cubic centimeter, including one that says per cubic centimeter. So if you have meters per, I don't know, per liter, I don't know, just make up anything. It doesn't matter. It'll all work, right? So, and the reason all these things are available as autocompletes is because behind the scenes in the framework, you'll see what looks like an absolutely ridiculous mess of functions and computed variables. There is a lovely set of regex scripts generating all these things. They're not maintained by hand. So adding new units, it can be incorporated immediately into the framework. And you can make your own custom units that will, with the generator script, it will build it into the language for you, and then you have it from then on. You can just make up whatever you want. And down below is just an examination of, once you do that, you can use them for converting to different units. It's interesting, in the history of coming up with all these notions, the different fields that all felt that they needed to have this particular problem addressed over and over. From psychology, some of the most important stuff came from people trying to do experimental psychology and running up against the question of, fundamentally, what is a measurement? And having to come down to, like, how do we treat measurements and how do we go forward? To biology, to chemistry, and other things. And they didn't foresee all this computer stuff happening back then, because it started like late 19th century, all through the 20th century. This was types of things that were concerning people about what is convertible and what are the fundamental dimensions to deal with. This is an example of mixing dimensions, a little bit of smaller font because it's taller. I wanted to point out how stuff is handled. Originally, when this, as a matter of fact, Ajaz and I did an early walkthrough, basically. We were giving presentations together where an very early version of this was done. And optionals were used when you tried to do basically everything. So you had to check everything as it was going through, and making an example piece of code even looked ugly. So nobody was going to adopt it for real code. So taking a tip from how numbers are actually processed when you do stuff, If you divide something by 0, or if you throw a bunch of numbers into something and you manipulate them in such a way that you don't actually produce a number, in doubles you get a not a number. So here we have the equivalent, which is not a thing. And you can even ask a thing, there's a property called is a thing. And you can ask for that if that ever is a concern where you're doing something very dynamically and you want to be able to check it at runtime. But here, force plus mass, not a thing. And if you take force plus mass and divide by 7 feet, still not a thing. So it cascades. Now, the nice thing is, and this will come up, is there's a way to track your problems down and find out where the problem happened. And I'll get to that in 1 second. But you can ask for what's called a dimensional description of a given thing, where you're not given the answer in terms of specific units, which might be confusing in some cases. There's a standard way of representing the dimensions. And here, for force, it says length to the first power, mass to the first power, time to the -2 power. And the last thing I'll point out here is that you can, for any given type of quantity, you can ask for it in the base units so that you can make sure, you could say that, you know what, I don't know what an erg is. It's a cool unit name, but I don't know what it is. So you can ask for it in basic SI units and it'll tell you. So another mixing example here is, let's see where I am. All right, so in terms of angles, you can do something like this, where you take an angle over time so that you have some sense of rotational velocity or something like this. A slightly bigger example of angles, and this is something that is a good example of something that, for people who don't deal with numbers, but at some point you're going to rotate a piece of graphic or something like this. Well, there's actually a broad class of unspoken bugs, because everybody's embarrassed about this one, where if you mess up a trig function, you're doing some trig and you got a number and you're like, do I multiply by pi and divide by 180, or do I multiply by 180 or divide by pi, or sometimes I don't have to do anything and I don't remember why. And I'll see people just try 3 different things until they get the end result that matches what their expectations were, right? So this takes advantage of the fact that, you know, sine doesn't just take doubles. That's actually not what sine does. Sine takes a thing in a unit. It takes radians, and it produces a double. But it does not take just a generic number. So this honors that. So if you have a physical thing in any angle unit, so 75 degrees. Again, my keyboard, actually, most keyboards have that little thing. So you can, that is typable on a regular QWERTY keyboard. You can say something 75 degrees, take the sine of it. You can take the arc sine, which that's the inverse sine, so unwrap it back out, and you will get it back in radians. And then you can then ask to see that in degrees if you want. You can, so now you can say something like, I want to go 2 pi over 5, because you can kind of visualize that in your head, you know, like 2 pi over 5, you know, or something, whatever you need. Or you want to go full circle, you're going 2 pi. And so in that middle thing, I write the same, it's the same degree in 3 different ways, right? But down below, when you take the sine of it, you're guaranteed to always get it right. So all you got to do is get into units, however, and you don't have to stress about what happens in the sine thing. Also, I argue this is more readable, and you're going to not have any bugs at all in this code. Or at least, you got to go out of your way. Can never guarantee that part. So nice thing also, taking a cue from things that happen in the Python world and MATLAB and Mathematica and such, deals gracefully with arrays. So you can give a unit to an entire array of things. So, and it can be something, in this case, we got a bunch of files that we're going to try and understand a little better. So we're getting it in gigabytes. We know our data rates. So I can ask for how long is each one of these going to take to download. And so and I have it to whatever accuracy I decided I needed that in. There's a function in Python. I don't know if anyone uses NumPy, but NumPy has some really clever things. And one of the things they have is this idea of a linear space, where you can chop up a range either by giving the increment of the range or by how many things you want in the middle. And so I made the equivalent of that, which is a ramp function, because I think it's a little more descriptive of what's going on there. And that you can use this ramp to then get a group of angles together. So down below, there's a whole giant array of 27 different angles. And then I can pick one of those angles out, and I can take the sine of it. I can take the sine of the whole block of them at once. And here's the neat part. All of the stuff that gets done with arrays is going to use the accelerate framework, so it's all going to be hardware accelerated. So there's some neat little tricks that you can do that now you can have a team use who doesn't want to learn or never learned how to use any of the hardware acceleration stuff. You can just tuck it under the hood in this. Beautiful code, doing powerful stuff very, very fast. There's also a pretty neat thing that I think is unique on how it handles exponents. So the exponent type is not a double or an int. It's what I call a tiered number, which gracefully degrades as needed from integer to a ratio to a double if absolutely needed. And so what it allows you to do is do things like in this middle example where x to the 5th power, and then well, that's an example of just taking something to whatever power you would like. But in that y to the 3/7 power, I don't know why you're going to want something to the 3/7 power, but if you take it to the 7th power, it will perfectly take it back out to the power that you need. So in a lot of science, this is absolutely necessary. I saw a 5-minute thing, so I'm going to go a little quicker here. You can see this in the playground. You can do things to standard functions that you use right now. The u-second function. Quick, is that 30 milliseconds or microseconds? I can never remember. But it'd be nice to not even think about it. Just pass in the time you want. Just as Swift would try to unwrap an int and give you a nil, this is the one place where I use optionals. There's a strong typing system to this. So the one before is a dynamic typing system, what I've showed you so far. But there is a strong typing option, so you can strong type your functions. And I don't think I have time to really go into that right now, so I'm going to kind of blow through some of this. Sophisticated example here, I'd be happy to talk about it. We have real root functions that go into these things. There are interesting lessons to be had in here, and if anyone wants to contact me and talk about it, you'll probably be sorry, but I'd be happy to talk to you about it. There are neat different ways to write a square root. You can use the real square root function if you want to make your formulas look real. That's typable also. Most people don't know. But and here, if you're using a third-party thing and you're like, oh, well, I got to use this C function, and I've got all this wave data, and you can just to make, let's say you got a gigabyte of wave data about how high the waves are and stuff. You could turn it into a physical object as a group. You're all in feet, because that's how I measured you. And it'll figure out standard deviation, and it'll set your sig figs accordingly. And you can ask it questions. And then it's easy to then just extract the values, the whole array right there, send it to your C function. You didn't have to change anything about the C function, get your result back, and you can even convert it to meters at the end. Again, hardware accelerated. So you get some free things, even if you are using third-party libraries that will never conform to a unit system. And lastly, I'm going to just point out this thing where I set up some simple, in this system, physical objects. And I should mention at the top, you see how the constants are being set up at the top? I didn't put 9.81 meters per second squared. It has a rich set of constants that you can grab, and they are known to the best accuracy that they are all known. So that is the best value of sun. You're not going to get a better value of sun than that. And it has the uncertainty levels in the constants. So these are being generated by various sources, standards bureaus, and stuff like that. So taking some stress off anyone having to know these values. There's an experimental geometry branch of this thing that needs a little more love. And you can write code like you would normally write code for iterating through an animation. And when you run this thing, you can have something that in live time this is a thing of Halley's Comet. which came around a few years ago. And so I've got all these equations going on, and none of them are doing it in miles per hour, but I can get a live animated thing of miles per hour. I can get the acceleration in terms of Earth gravity, and I can get the distance from the sun in terms of astronomical units, none of which I had to actually calculate as far as the conversion factors between these things. And you can have them change on the fly. And it's so, since I'm already probably a couple minutes over, I'll just mention that there's some future directions. There's a crazy fascinating topic of, there's a notion of a kind of a quantity. So even if you match units, you're still different, you're too different. It's Romeo and Juliet, it can't work. And so, the system is going to evolve to handle this higher level of quantity understanding. A more flexible base value type, including complex numbers and ideally arbitrary underlying base types. To attack dimensionless quantities. And these are topics that are all fascinating, but would be a whole nother topic talk. Directly addressing geometric systems and having swappable geometries. And a rich metadata system. One thing I didn't have time to address that can happen if you get something that, if you're playing in the playground and you get not a thing, you can type that variable name and do dot and put error stack. Error stack, it's hard to say. And it will give you the full list of times that it banged into some other object and produced not a thing. It gives you a traceback of why that thing's not a thing. And you can trace it back to the moment it became not a thing. So there are a lot of rich things and a lot of pipe dreams that can go on. Sorry. I just got the 0-minute sign, which is great. Anyway, so this is, if this interests you, I highly encourage you to join the cause. I want this to be a thing that to be done with others. Input style, I could, pull requests, but also discussions about what is the best thing, what are my needs that are not being addressed by this, or what's being done wrong, or I'm a language expert and I can tell you how to do this one thing way better than you're doing it. I'm not a language expert, so this is where the GitHub lives, and well, this project's GitHub lives, and I highly encourage you to take a look, and whatever feedback you have, I would love to hear. I think technically we have a couple minutes.